didn't draw it very good, but hopefully after my idea explain it, you guys can understand it. Okay, so the idea of, before we talk about the self-calibration bundle adjustments, let's talk about the bundle adjustment itself. It's actually, bundle adjustment itself is actually a very important solution, and actually it's the, you can say the most widely used, most widely used solution in the area of geometry. So the idea for the bundle adjustment is that you are going to take the multiple images, and those multiple images, they are highly overlapped with each other. They are overlapped with each other. So as you can see, you are taking multiple images like that. And so in this case, when you are, and also, well, in this case, as you can see, I intentionally draw some feature points on the, in the image space. And when you are taking those highly overlapped images, then those points will appear on different images, right? So for example, like this one appear on E1, 2, 3, three images. So they will appear on multiple images. So in this case, they can serve as the control information. They can serve as the control point information to connect those images together. Let me finish what's the purpose for the bundle adjustment first. The bundle adjustment, okay, then let's talk about that first. The purpose, like what bundle adjustment is it's an approach that can help you to obtain, that can perform the space resection and space intersection in the meantime. Right? Let me talk about it again. So bundle adjustment is a solution that can help you to obtain the camera location and orientation. So camera orientation, and also object space coordinates in the meantime. Right? Just calculate at once, and you can get everything. So which means that when I take those photos, I don't need to know the EOP. I don't need to know the EOP. And there are a lot of unknown object space coordinates in the object space. But I just need to take a lot of overlapped images, and I perform the bundle adjustment. Then the output from that can give us the EOP and the object space coordinates. Right? So it sounds magical, right? So because we talk about, say, well, you either don't know EOP, you either don't know object space coordinate, or you don't know image space coordinates. Then you should know two of them to obtain the third one. But bundle adjustment can help you to obtain EOP and also object space coordinates in the meantime. Just one process and to get those information. So that's the magical part. So how exactly does it do it? So as you can see, this part is important. So basically, as you can see, in order to get let's break it down. Let's break it down to each individual unknowns. If I want to know the EOP for this photo, for this image, then I need control points. You guys know it. We need control points. So as you can see, we have a lot of object space coordinates over here, object space over here, feature points over here. Of course, right now it's unknown. The location is not known. So, but however, we have nothing. If we know those coordinates, then we can obtain the object space. We can obtain the EOP for this. And same goes to others. So we have a lot of feature points, but we just don't know the object space coordinate yet. We just don't know it yet. And then for each of the object space coordinates, for example, like this one, it's taken by 1, 2, 3 images. So we supposedly, if we can know the EOP, then this can be solved with space intersection, because 2 images is enough. A stereo pair is enough, and not to say 3 images observing these points. So supposedly, if we know EOP, then we can obtain that. So the problem right now is, how can we know them at the same time? Right? How can we understand the performance of them at the same time? So in this case, we can talk about the number of unknowns that we have. And also, alright, first of all, if right now I set it up as the relative coordinate system, if I set it as a relative coordinate system, I said, okay, this one is 0, 0. And for example, this one is 100, 0. For example, x and y coordinates. I set it up as a, well, not random, but however, it's a local, and pseudo coordinate system. Then they become control points. These 2 points or 3 points becomes the control points. And then everything is integrated into one system. And with those coordinates, with those object space coordinates, then we can obtain the EOPs. And after we have the EOPs, then those unknown object space coordinates can be solved as well. So, but however, you may wonder, say, this will be in the fake coordinate system, right? Because we just assign, say, this is 0, 0, this is like 100, 0, and we just set it. We just set it by ourselves. But we, of course, we need to define, say, for example, this is 0, 0, this is 100, 0, and this could be 0, 100, for example. We set the 3 control points over there. So, but however, you may wonder, say, in this case, everything is in one system, but however, their coordinates is not the absolute coordinate system. It's not the real world coordinate system. So, what we can do is to use the real control points. So, maybe we can identify some of the features. They are control points. They are control points with the absolute coordinate that we obtained somehow. Maybe measure it from a GPS or from some surveying technology, so we can get the coordinates. So in this case, we can use those control points to control, or you can say to move the system, to move the whole system, and then register it to the real world coordinate systems. So in this case, the EOPs becomes the real coordinates, and the object space coordinates becomes also the absolute coordinate system as well. Okay? So the boundary adjustment purpose for that is to combine everything together. So the most significant advantage of boundary adjustment is to combine everything together to obtain the most probable value at once. To get the most probable value for the EOPs, for the object space coordinates at once. Okay? So basically that's the solution for this. That's the solution for this. We haven't touched the mathematical detail for that for the boundary adjustment. Actually, we have that on the slides, but we will talk about that in the future, but not now. Actually, not now. So till now, any question? If no question, then let me ask another question. If without using boundary adjustment, how can we get the EOP and the object space coordinates? We are going to perform the space resection first, and then perform the space intersection later. So 2 steps. It becomes 2 steps. Boundary adjustment is 1 step and give you everything. And 2 steps means first, because eventually we want to get the object space coordinates, then we need to get the EOPs first. So we need to perform the space resection and then perform the space intersection. So how to perform the space resection? Of course, we need to have some control points on the field, and we can perform the space resection and to obtain the EOP. And after we have that, then we can measure those. We can measure the object space coordinate. We can measure the feature points on each of the image, and then perform the space intersection to obtain them. Okay. So that's the 2-step process. Let's compare them. The 2-step process. First, the resection, intersection is the 2-step process. The other one is boundary adjustment. Combine everything together and solve it at once. What's the differences between these 2 solutions? this is a little bit complicated, so I think I'll give you a little bit more time, like 15 seconds. Okay, so what's the difference between these two types of solutions? What's the difference? There. Two-step process and one-step process. Any difference between them? Or they will give you the same result. Do you? Do you want? Okay. On. Right.
I haven't got anything.
Deborah?
Maybe the error when we do the space intersection will move when we perform the space intersection.
Will be what? Will be moved?
Will be included when we perform.
Okay, so but however, when you are doing the bundle adjustment, won't the arrow include it?
But it's in one time, so the error is.
In one time, so the error what? Actually, you are on the your answer is very close to the well, not close. It's on the right track, but so. You mentioned there are some error, right? There are some error, and then if you do the space protection first, and there's the EOP has the error, and those EOP has the error when you perform the space intersection. The object space coordinate also has error, and yes, but well, once you if you have errors, then your bundle adjustment also has error, right? So in this case, how does it differ from each other? Deborah, any thoughts? Your direction is correct. It's on the track, on the right track. Any thought? Yeah? Angie? So,
I have no idea.
think about the arrow. Think about the arrow, yes.
Other than this
Lens distortion, they are the same camera. We haven't touched the lens distortion yet. We haven't touched it, but they are the same camera. Going. Yeah, error propagation. Yeah, we kind of like talking about that. So what do you mean by that?
Because the two steps is to do the intersection and recession and intersection.
Hmm.
So the error of recession will go into the
Will be propagated to the intersection. Yeah. So like Deborah mentioned, right? So what I mean is, on the adjustment, you also have the arrow, right? So the arrow is over there. It's over there. How does it differ from like the two-step process? Any idea? No? Okay. So anyone? Someone?
maybe figure out.
Okay. So actually, the idea is like this. Zhongying and also Deborah are correct. So when you are performing, like for example, like two-step process, then your EOP will have some error, and those error will propagate to the space intersection, and then so your object space coordinates also have error. But it's the same thing goes to the boundary adjustment. There are error over there. So, but the thing that the boundary adjustment does well is everything is combined in one single system. Everything is combined in one single system. So in that system, it gives you an answer that is the most probable value that can achieve the residual summation, the residual square summation minimum. So that's the answer, and can help you to achieve that. So, but why the two-step process is not so good at that? It's because if you perform the space resection first, this has its own error. Because when you are performing the space resection for this, you will use a set of control points, and that set of control points has its own error. When you perform the space resection for this image, you will have the other set of control points, and that set of control points will give it another error. So individually, each EOP has its own error behavior. For example, error behavior means that this EOP may have an error in the x direction shift. This EOP may have an error in the omega phi kappa phi rotation, and this one could have a little bit kappa rotation. So each of them may have its own individual error behavior. So like you guys mentioned, these EOPs have contains error.